This is the Flash. You know him, you love him, he runs around the DC universe, and let me tell you, he's pretty darn quick. But just how quick is the Flash? Well, this all depends on which comic you look at. See, DC have never said what the Flash's top speed is, and depending on where you look, you can get an answer from 10,000 miles an hour to 10 trillion miles an hour. Now, 10 trillion miles an hour is a little too quick. There is one speed which the law of physics doesn't allow the Flash to pass, and that is the speed of light. The speed of light, commonly written as c in physics, clocks in at 300 million meters per second. That's just over 1 billion kilometers an hour, or 670 million Great British miles an hour. In other words, pretty darn quick. But let's set one thing straight. The Flash can't actually go at the speed of light. See, in order to go at the speed of light, he would need an infinite amount of energy. Not a lot of energy, but quite literal infinite amount. The only thing that can go at the speed of light is, you guessed it, light. And that's because light technically has zero mass, and 0 times infinity is an actual number. Just trust me on that one. Okay, so we know the Flash can't go at the speed of light, but what if he could get pretty close? I mean, Dettol only kills 99.9% of bacteria, and well, everyone acts like it kills all bacteria. And if you got stopped by a cop and he said, "Madam, do you know you were doing 100 miles an hour in a 30? And you said, "No, technically, officer, it was only 99.9 miles an hour, you'd still lose your license. So, what if the Flash could go at 99.9% the speed of light? Well, in short, you'd die. This is because at this insane speed, all the air molecules around the Flash would be stationary. In order to move through the air, the Flash has to move these molecules out of the way. The molecules wouldn't have time to move out of the way, they'd crash into each other, and things would get a little bit nuclear. There is a very good XKCD comic on this. I'll leave a link in the description below for those that are interested. Would recommend reading it. But for the purposes of this video, I'm going to assume that the Flash's suit somehow neglects all air resistance and fusion effects so you don't die like this. I mean, come on, his speed comes from the Speed Force, so the suit's gotta have something special in it. So, what would you see? Well, there's 4 very interesting effects that would happen. I'll go through them in the rest of this video. Imagine a train moving towards you. As it gets faster and faster, what you'll notice is the train will get shorter and shorter in the direction of motion, approaching almost 0 thickness as you approach the speed of light. Now, at 99.9% the speed of light, the Flash would have a Lorentz factor of 22.4. That number will be important later. The, depth of an average human is about 20 centimeters. At this speed, you would only see the Flash to be 1 centimeter deep. That's about the width of your human finger. That means this entire body that you see moving towards you would only be about 1 centimeter deep. If you add another 9 to Flash's speed, make him go 99.99% the speed of light, he would shrink to only 0.3 centimeters. That's about the thickness of a pencil lead. Yet another 9 makes him about the width of a grain of sand, and if you wanted to make him as wide as an atom, which you theoretically could, you would have to be going 26 nines there, percent the speed of light. Take 2 stopwatches and start them off at the same time. If you send one off into space at a low speed and the other at a high speed, you'll notice time actually passes differently for the 2 stopwatches. The one going at a high speed will tick slower. This effect is called time dilation, and it means the faster you go, the slower time passes for you. So how will this affect our Flash? Well, we know the circumference of Earth is 40,000 kilometers. At 99.9% the speed of light, it would take the Flash only 130 milliseconds to do a lap around the Earth. But this is where time dilation comes in. After the Flash has done his lap, you go up to him and say, "Good job, Flash, that only took you 130 milliseconds, which is about the reaction time of a human." But the Flash would go, "No it didn't, it only took me 5 milliseconds, because time has been passing slower for him." This means if the Flash could run at this speed for an entire year, everyone on Earth would age by a year, but the Flash would have only aged by half a month. But a year is a bit of a long time to be running. I mean, the Flash, he's a superhero, but let's cut him some slack. So let's say the Flash, in his frame, has been running for a minute. How long would we see him running for? Well, 22.4 minutes. Not all that impressive. What if he was running at 99.99% the speed of light? Then we'd say he was running for just over an hour. If you add another 9 there, you'll see he's been running for about the length of 2 movies. And in fact, if you set the Flash's speed as 99 point and then 23/9% the speed of light, we'll see him running for an entire 100 years. This means the Flash will have only been running for a minute, but on Earth, most of his friends and family will be dead if we haven't cured aging by then. You can see the Doppler effect in your day-to-day life. Imagine you're standing on the side of a street and there's an ambulance passing you. What you'll hear is the following. Nino, 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 Nino. The pitch of the siren changes, even though you know the siren is making a constant sound. So why is this? Well, it's because the ambulance is moving. As the ambulance moves towards you, it squashes the sound waves, so you hear a higher pitch, and as it moves away from you, it sort of stretches them out, so you hear a lower pitch sound. Now, light is just a wave, so the same thing happens with moving objects. If they're moving towards or away from you, their colour will be shifted along the visible light spectrum. So how do we work out what their new colour will be? Well, luckily, there's an equation for that. But in order to use this equation, we need to know the wavelength of light that Flash's suit emits. Now, the Flash has a very distinct red suit. The wavelength of your classic red is 620 to 700 nanometers. But Flash's suit is a bit darker than that, as you can see from the picture, so we'll say it's 720 nanometers. Plugging the numbers in, we see that when the Flash is moving towards you, you will have a wavelength of 16 nanometers reaching your eyes, and as he moves away from you, 32,000 nanometers will reach your eyes. Now, the first of these numbers is firmly in the ultraviolet spectrum, and the second is in the infrared spectrum. This means that the Flash would actually be invisible to the human eye, and all this stuff I told you about length contraction earlier is a bit useless because you wouldn't be able to see him. In fact, this effect is so strong that even if the Flash was only moving at half the speed of light, as he moves towards you, his suit would be very blue. This last effect is essentially a massive optical illusion by physics. For it to work, the Flash has to be moving across your field of view. So, the setup for this is very different from the other effects where he was either moving towards or away from you. Here he's moving side to side. Because the Flash is moving so close to the speed of light, there's a pretty large time difference between when light is emitted from the front of the Flash and the back of the Flash. This means when the light reaches your eyes, the Flash will actually be rotated. At 99.9% the speed of light, he will be rotated by pretty much 90 degrees, which means when you're looking at him past your field of view, you will see something like this. The Flash would be moving side to side, but you would see him almost running towards you, as if you were on ice. This would be very strange indeed. There is one last effect we might need to consider though. If you're just in your car, it's a regular day and you want to get from point A to point B, you generally want your car to move forward. Well, how does the car do that? It's simple. The car pushes back on the Earth, and then according to Newton's third law, the car gets pushed forward, and you can drive around the Earth and go along your merry way. The same thing happens with the Flash, except this force has to be much, much larger. So this begs the question, if the Flash sets off on the equator, could he actually speed up or slow down the rotation of the Earth and make the days longer or shorter? Well, we have all the numbers here. If we plug them in, we see the Earth does not care. It is really big and really, really massive. Like, the Flash is going pretty fast, but it's nothing compared to the mass of the Earth. In fact, even if the Flash ran at the Earth at 99.9% the speed of light and punched it with all his might, it would not flinch. The people around him, though, I don't think they'd appreciate the gesture.